Hey guys, so we're going to pick up with Half-Life, which is really where we left off with the nuclear stuff from before. Hopefully, you watched the video that I posted on the classroom regarding an introduction to Half-Life and what it really means. But in my words, um, basically, Half-Life determines how fast these nuclear decays occur. So if you have a really short half-life, something that maybe is 1 second, every second half of the sample is decaying and giving off those particles. That's a pretty unstable situation. The faster a decay is occurring, the more unstable that reaction is. Then you have things like carbon 14, which has over a 5,000 year half life, meaning it takes 5,000 years to go from having the full sample of unreacted carbon to half of that. And so that's half life. Like, by definition, that is half life. How much time it takes to get to X amount of grams in a sample. So there are two ways that we can look at this, and we're going to be, well, really three ways. I'm going to be showing you the mathematical steps the way I teach it in a moment. But in any half-life, it's basically a basic sample. So you start with 100%. So in the video, you can see that this yellow amount or yellow bar represents unreacted sample. And the half-life, one half-life, is the amount of time it takes to go from a full sample being unreacted to half of the sample being unreacted, or half of the sample being reacted, right? So you have half reacted and half unreacted. So this process doesn't just stop. It just keeps halving and halving and halving as each half-life period occurs. One of the jokes that my grandfather used to tell me was, if a rabbit's 10 feet away from a tree, and every time it hops towards the tree, it gets halfway closer, how many hops is it going to take for the rabbit to reach the tree? And, when you jump the gun, you just say 2, 5 feet, then 5 feet. But the rabbit analogy is, the real answer to that is that it never reaches the tree. Because each time it gets halfway, it's an infinite amount of times you can divide a number in half before you get to zero. I mean, half-life is the same way. Remember, atoms are tiny, like smaller than this little space between my fingers. And even if I had 0.000000001 moles or 10 atoms, the half-life that went on beyond that would just be half of it. So we're going to look at this in two ways. We're going to look at it in fractions, as you've seen here, right? Half of the sample is left after the first half-life. Then half of a half is a quarter. After 2, the third time through, it's an eighth. The fourth time through, it's a 16th. And then a 32nd, and a 64th, and a 128th, and a 256th, and a 512. I think I did that right. And so we're going to look at it in fractions, but we could also look at it in grams. And we haven't, in this general statement, it's not been given. But for instance, let's say we had 1,000 grams to start with. Well, if after one half-life I have half of the original unreacted sample, that would be 500. And if after a quarter, that would be 250. And after a third half-life, having 1/8 of the original 1,000, I would have 125. And if after a fourth half-life I went through this, I would have 670. Oof. I got to go back to school. 62.5. All right. In fact, that just continues to go and continues to go and continues to go. And the third way that we can measure half-lives, which you're going to see in a second, is a time question. How much time does it take for 125 grams of this sample to be given? Sorry, let me try that again. How much time does it take for 125 grams to be unreacted if we started with 1,000? And there's one piece of information missing from this, is what is the time of this particular half-life? I'm just going to arbitrarily write in 1 hour. It'll make it easy, right? So what that means in time is if I have my original sample, I start with 0 hours. And after 1 hour, I'm going to reach the first half-life. So this situation right here, 500 grams would be left after 1 half-life, which would take 1 hour. Very, continuing along, if another hour took place, I would be left with a quarter. So now, 1 hour plus 1 hour, which would be a total of 2 hours. That's total. This is each time. 1 hour to here, plus 1 hour to here, plus another hour to here. It would take 3 total hours to reach 125 grams, or 1/8 of the original sample, if I started with 1,000 and the half-life time was 1 hour. Okay, so this is just all stuff that I kind of made up as we are going along here. So this brings me to a very important table on the reference table. So let me pull that in here. We're going to look for table N. There it is. Table N is called selected radioisotopes. Table N looks like that. Looks great. So let me just break this down for you. What we're looking at here is a lot of information. We've got the nuclide, which gives me the symbol and the mass. These two tables, nuclide and nuclide name, mean the exact same thing. So AU with a mass of 198 can be called gold 198. So what's nice is they give you two representations of the same thing, bookending the table. The other thing that we're just learning now is about half-life. So once I know which things that I'm talking about, which atoms, which radioactive isotopes I'm talking about, now I can figure out how long it takes for them to decay. So I have, I was just mentioning carbon-14 has a really long half-life. Carbon-14's half-life is 5,715 years. It's a pretty stable radioactive isotope, which is very different from something like calcium-37, which has a half-life of 182 milliseconds. So, if these atoms had feelings, it would almost be like calcium would be radioactive to the 1/1000th fraction before carbon even thought about becoming radioactive. It's every isotope can happen at a different speed, and those speeds are designated for you here. And the other thing from last week that's cool is now, you can be asked things like, what type of decay happens for potassium-37? And you'd be like, how the heck am I supposed to know without a formula where I can figure out the particle that's given off based off of atomic numbers and how it changed? Well, you don't have to do any of that, because you could just find potassium-37 and find out, oh, that's a beta plus. And then you can proceed, however, through a situation like that. All right, so this is table N. It's going to be really useful in the next coming lesson, so make sure you know it's there. But let me just try and show you my two methods to solve this. Hold on. I dropped it. So, question reads like this. How long will it take for 100 grams of potassium-42 to decay to 12.5 grams? So I know where I'm starting. This is my original. I know the end unreacted that I want. And I know the isotope. But the question's asking me how long. I need to know the time. That's what I'm looking for. Time is my variable. Time is what I want to know. I don't know. How am I supposed to know that? I don't know how long a half-life is. Potassium-42 has a half-life of 12.36 hours. Okay, I'm going to write that down in the corner here. 12.36 hours. And so basically, every half-life takes that long. So there's two methods, arrow and box. Arrow is a little bit more straightforward. Box is more comprehensive. So if I had 100 grams, is where I start. The arrow is one half-life. One half-life. How long did one half-life take? 12.36 hours. Well, how much mass would be left after one half-life? Half. Okay, well, that's not my end amount. I don't need to know that. So I must have went through a second half-life. So the second half-life is another 12.36 hours. That would leave me with 25 grams. That's still not 12.5. So I must have at least gone through a third half-life plus another 12.36 hours. If I went through that, I would be left with 12.5 grams. So by just arrowing across, I figured out that I went from 100 to 50, 50 to 25, 25 to 12.5, 3 half-lives. So it was 12.36 hours, another 12.36 hours, and another 12.36 hours, 36, 37, 36, 37.08 hours. That's how long it took for 100 grams of potassium-42 to decay to 12.5 grams. All right. The box method, a little bit more comprehensive. There's 4 titles in the boxes. There is the mass, there is the time, there is the number of half-lives, and then there is the fraction. You don't always use all of them, but it's always good to know what they each are, what each of them are. So we just kind of fill in as we go. So the mass at the start was 100 grams. The time at the start was 0. The number of half-lives at the start is always 0. This and this always start as 0. The fraction is 1, because you have a 1 over 1. All right. So what happens as I go through the first half-life? Well, the amount of mass that I had here cuts in half to 50 grams. The amount of time for this particular isotope was 12.36 hours. So I add that to my time. And the fraction was a half. I went from 1 over 1 to 1 over 2. I go again. After the first half-life, I go to the second half-life. 50 grams has now decayed into 25 grams. How long did that take? Another 12.36 hours. What's the fraction left over? Well, if I cut 1 in half, it's a half. If I cut a half in half, it's a quarter. I do it again. What happens if I go through a third half-life? I go from 25 to 12.5. How much time did that take? Another 12.36 hours. What's the fraction? Now it's 1 over 8.